In today's class, we will learn about how to solve a second order homogeneous differential equation. So let us start by writing a general second order homogeneous differential equation, and I denote our constants as p's. So we rewrite this equation by scaling by the constant p2. Since p0, p1 and p2 are constants, so the fractions p1 by p2 and p0 by p2 will also be constants, and we can redenote these constants by some other denotion. Let us choose letter small k to denote our two fractions p1 by p2 and p0 by p2 with different indices. So we can rewrite this equation as let p1 by p2 be another symbol k1 and p0 by p2 be denoted by another symbol, say k0. The next thing which we do is we have an operator first differential with respect to x. So we can denote this differential operator by a symbol capital D and rewrite our differential equation in terms of capital D. So this becomes d square, that is apply d by dx twice, which gives rise to second order of differentiation with respect to x. It can rewritten as so we have a function of capital D operating on variable y equal to 0. So this is how we can represent our second order homogeneous differential equation as. And equation number 1 is called the auxiliary equation if we put f of d equal to 0. From equation 1 it is very evident that y cannot be equal to 0, so f of d will be equal to 0, and that equation is called the auxiliary equation. So from the same equation we say that it follows f of d is equal to 0, and this is called the auxiliary equation. Auxiliary equation is a second order equation, or it's a quadratic equation, so it will have two roots. Let us denote those roots by small m1 and m2. So we can rewrite this as, it means d minus m1 d minus m2 equal to 0, where m1 and m2 are the two roots. Let us denote this equation by equation number 2. Now since m1 and m2 are the two roots, they can in general be of any type. It means that either both m1 and m2 are real. Further, m1 and m2 can be equal or unequal, or m1 and m2 are not real, that means they are complex. So this gives rise to three sub cases. The first case will be when m1 and m2 are real but not equal. Second case one will be when m1 and m2 are real but they are equal in magnitude. And the third case will be when these roots m1 and m2 are complex. We will take all these three cases one by one. So, our first case is when m1 and m2 are real and they are unequal in magnitude. When this happens, re-look at equation number 2. And equation number 1. So, if we substitute 2 in 1, we will get d minus m1, d minus m2, y is equal to 0, such that m1 and m2 are real and not equal. So, this will imply either d minus m1 on y is equal to 0 or d minus m2 on y is equal to 0. Both these two equations are first order differential equations. We can easily solve these equations. dy by y is equal to minus m1 dx Let me denote our y0. I was using y0 for the constant of integration, but I will not use y0 as it. I will use variable c to denote the constant of integration. So, c1 is our constant of integration. So, y will be equal to c1 times exponential m1x. Similarly, this equation will be leading us to y is equal to say another constant of integration c2 exponential m2x. To keep this equation and this equation as separate, we will use index 1 here and index 2 here. So, the two solutions which we have is y1 is equal to c1, which is a constant of integration, exponential of m1x, or the second equation solution we get is y2 equal to constant of integration c2 exponential m2x. Since our original equation is a second order equation, so the final solution will be linear combination of y1 and y2. So, our final solution will be y is equal to so this will be the complete solution to the differential equation. If m1 and m2 are real and they are not equal. So this will be your complete solution. Let us number this as equation number 3. Let's take the second case where m1 and m2 are real but they are equal in magnitude. When this happens, our equation, which was f of dy equal to 0, this equation, first equation, this will be rewritten as d minus m times t minus m on y is equal to 0. Let d minus m on y be represented by z. So when we substitute here, this will become d minus m on z is equal to 0, which is a first order differential equation, and we know the solution. The solution will be z is equal to, say, a constant c1 exponential mz, so mx. Now substitute back what z was. It was d minus m times y. This is equal to c1 e to the power mx. Let us simplify. If we have to solve such kind of an equation, we know that such equation can be solved by choosing appropriate integrating factor, and the appropriate integrating factor in this case will be, this is our integrating factor, which will be equal to e to the power minus mx. So let us multiply this if on both the sides. When we do that, our differential equation becomes an exact differential equation, and it will be easier for us to find the solution. So on the left hand side, we see that we have a complete differential of function y e to the power minus x, which is very simple to solve. We will have integration on both the sides, which will give us our solution in this case will become y is equal to c0 plus c1x, where c0 and c1 both are constants of integrations, and the value will be evaluated in the questions from the initial conditions which are given. So this gives rise to another equation. Let us see which number. It will be equation number 4. So we have equation number 4. This was for the case when our both the roots are equal in magnitude and they are real. So we have done first two cases. Now we will do the last case when the roots are complex, which will be our third case. So this means m1 and m2 are complex. If m1 is represented by alpha times iota beta, then m2 will be the complex conjugate of it, where alpha represents the real part of the root and beta represents the imaginary part. Now these two are complex roots. What we will do is we will substitute the values of m1 and m2 in the solution we get from case 1. So let us rewind. Let us go back and see our case 1 solution. Our case 1 solution was equation number 3. We will start from this equation number 3 and substitute the value of m1 and m2 here. So what we do is put in equation number 3 and we will get then we will open the exponential term. We know that exponential iota beta x will be equal to cos of beta x plus iota sine of beta x, and exponential minus iota beta x will be equal to cos of beta x minus iota sine of beta x. So we will just put that. So simplifying, we get equation number 5, where capital A1 is equal to the sum of constants C1 and C2, and A2 is equal to C1 minus C2. So equation number 5 will be the solution to the second order homogeneous differential equation if the roots to the auxiliary equation are complex. So now we know all the 3 solutions under the 3 cases, and we will apply these 3 solutions when we solve our questions. Let us list down the questions which we will do. So we will solve. I will write down 3 questions, 3 differential equations, one from each of these 3 cases, and then in the next class we will solve all these 3 questions. We will solve these three equations in the next class.